Dear colleagues, good afternoon. Welcome to the second Spotlight Talks organized by the Working Party in High Pressure Technologies. At the beginning of our meeting, I would like to give the word to the Executive Vice President of the European Federation of Chemical Engineering, Professor Jarka Glassey.
Thank you, Irena, and hello everybody. Good afternoon, good evening, good morning, wherever in the world you're joining us. And it's my great pleasure to say a few words at the start of your second of webinar series in our Spotlight Talks. Just a little bit of an introduction on me. As Irena kindly said, I'm the Executive Vice President of EFCE. I am originally from Slovakia. I graduated as a biochemical engineer, but I work as a professor of chemical engineering at the School of Engineering at Newcastle University in the UK for more years than I've lived in Slovakia. And as I said, it's an absolute pleasure to be here with you and to introduce this really interesting webinar this afternoon. Just a few words about our Spotlight series. So those of you who have joined for the first of the Spotlights for this working party will know that this is already a number of webinars that we've organized. In fact, this is the fourth year of this initiative that the European Federation of Chemical Engineers is running. We started in 2020 during COVID pandemic just to try to keep the community together. And we very quickly realized how successful these webinars are in bringing the latest developments in various topics in chemical engineering to the fore in terms of allowing people to join and listen in on interesting topics that they may not have otherwise attended, because physical conferences typically concentrate on very specific issues. And like this, we are enabling a bit of cross-fertilization between various specialist areas. So it's really nice to see that this time around, we've got 9 of our working parties and sections contributing to this series of Spotlight webinars. And over the next 2 weeks, really, with a little bit of an overrun, you can actually sample various other topics as well if you are interested in. We've got a mixture of industrialists and academic experts. And if you want to find out a little bit more about them, you can find more information on the EFCE website and register there. While you're on the EFCE website, you might want to find out a little bit more about EFCE if you don't know our institution or organization. And you might find that we promote scientific collaboration and support the work of chemical engineers in 30 European countries, which means that we represent over 100,000 chemical engineers in Europe, and actually some people from outside Europe too. For us, the working parties and sections are the major working heart, the scientific engine of this society, and they drive all of the EFCE activities in all the various aspects of chemical engineering that you can imagine. They provide a very important forum for technical exchange and also networking among chemical engineers in Europe. And I'm really pleased to see that in this particular Spotlight series, we will actually have first contributions from our 2 newest sections of EFCE, chemical engineering as applied to medicine and the early career chemical engineers. And I don't want to hold this up any longer, but before I conclude, I would really like to thank all of those within your working party, but also in the other working parties and sections and the EFCE in general, for making sure that we can continue with these really important initiatives and the Spotlight talks. And I think that particular thanks go to EFCE's Martin Pou, who is with us from Toulouse, who did absolutely the lion's share of all the conceptual and setting up and practical work that is necessary for these webinars to run seamlessly. So I thank you for your attention, and I wish all the speakers and obviously all the attendees a very fruitful and successful webinar. And now I would just like to hand back over to Irena to hopefully take us through the webinar program itself. Everybody enjoy it, and hopefully if you've missed any of the talks, you will definitely be able to find them on our YouTube channel as well. Thank you so much.
Thank you very much. So high pressure is a vast potential, and today we talk about its utilization in improving existing technologies, developing new ones, and meeting the demands of the modern society. During the first spotlight talks, Professor Cosero stressed the response of high-pressure technologies to the challenges of the 20th century. One of the most important being the limit in food production due to lack of fertilizers. The development of high-pressure Haber-Bosch process allowed for the ammonia and nitrates production on industrial level. There were also other important achievements on industrial scale in polymerization and in separation technologies. The application of supercritical carbon dioxide, which replaced fluorinated organic solvents, allowed for industrial processes such as coffee and tea decaffeination, production of hops extracts for the brewing industry, and obtaining the most natural aromas and fragrances. This technology nowadays moved towards the isolation and purification of highly bioactive natural molecules. High-pressure technology today has answers to the challenges and issues of the 21st century. It can completely eliminate solid waste and effluents in highly polluting technologies. Examples are leather tanning, a dry dyeing of textiles, and wood impregnation, where the application of supercritical carbon dioxide in these highly polluting technologies was a real breakthrough that completely eliminated wastewater. High-pressure technology today enables production of novel materials such as aerogels and novel catalysts. High-pressure technology today minimizes additives in foods, at the same time prolonging their shelf life. High-pressure technology today in processes such as supercritical water oxidation, hydrothermal gasification, and high-pressure hydrolysis utilizes biomass to produce energy and to produce chemicals, and what is very important, to separate phosphorus from biomass. And the last will be the demand for all biomass treatment units in the European Union in the future. Dear colleagues, in the frame of this huge potential of high-pressure applications, we have our talks today. I would like to tell you that you can, during talks, you can write your questions in Q&A or in chat, and then after each presentation, we will read some of them and answer. In case that you do not manage to get answer, please contact us. I would also like to mention that part one of this webinar called Technology to Improve Conventional Chemical Engineering Processes is available on EFCE YouTube channel, as well as this one will soon be. So we can start our talks now, and we will start with Professor Philipp Jaeger from Clausthal University of Technology, and its talk about the role of chemical engineer, about sustainable energy, high performance materials, and also education in chemical engineering. Philipp, welcome, and the screen is yours.
Yeah, thank you so much, Irena, for this very pleasant introduction. And I'm very thankful and grateful to be here It's a big pleasure, and especially also to open, let's say, the session. So I was thinking, what is adequate actually to open a session of like so specialized chemical engineers. And I thought something a little more general, the role of the chemical engineer during the energy transition and development of circular economy, which has a lot to do also with high pressure, as we will see. So just a little bit of background of myself. So I'm at this moment, I'm located here at Clausthal University of Technology at the Institute of Subsurface Energy Systems, which was the formerly petroleum engineering department here. And of course, during all this transition and the new trends, we also had to rename the institute, but still we're talking about like the diversity of energy. So yeah, we are, for those that are maybe not so familiar with this little city in the middle of Germany, it's right here in the. Can you see my mouse button actually? Okay. So here in a mountainous area called the Harz, which was formerly mining area, and this is how back in 1775 the mining school was founded, and from there, like everything that had to do with subsurface geology and mining petroleum was added to the school, and a technical university was formed. So the topics that we are dealing with are, of course, all subsurface processes involving fluids. Now recently, of course, the geothermal energy, also carbon capture, storage, utilization, and last but not least, hydrogen. What is needed is, apart from the drilling, which is more the mechanical engineering from our perspective of a chemical engineering here being at the institute, we have to do with material compatibilities of pipelines and all the equipment that is needed. You will see also, I will be talking a bit about polymer recycling, because part of the tubes liners are made of polymers. And what is my specialty is the system properties and interfacial behavior at process conditions. So let me also advertise a bit for our community, like what is so special about the chemical engineer. If you look at this really distinct program from today, you will recognize some of the points that I'm trying to point out here. So I would say, I hope you agree, my co-presenters here, that we know how to handle energy and mass balances. And we also have a slight like memory of what the second law of thermodynamics is. And this is why we have somehow also the thinking of process efficiencies incorporated, which is also reflected by one of the talks later. We have experience in linking fundamental research to applied science, discover analogies. This is something really neat. And cultivate a certain like innovative spirit, which is also reflected by all of the talks. And what I find now, as I said, from my perspective of a chemical engineering working with all of these disciplines in subsurface energies, we're not afraid of talking to other disciplines, which gives fruitful discussions and brings us further on. And the question is, what I'm trying to, let's say, incentivate here is, is how can this be made use of for our future developments? So I just picked out some examples to discuss about, like first of all, of course, the sustainable energy, some facts from the point of view of a chemical engineer about the sustainability and the currently discussed solutions. Then just a couple of slides about high performance materials and what we can do with it. So on the one hand, we're talking about sustainability, but on the other hand, everything has to be safer and cheaper and more efficient. And sometimes there's like some apparent contradictions in this. So how to deal with this? And last but not least, also the education. because what we're seeing here in Germany is we're running out of young people being interested actually in technology, and especially also in chemical engineering. So what are the key qualifications for future engineers, and how can we motivate them? But I advise you, like it took me quite some time to get through all of these statistics and finding some more or less like interesting numbers to present to you, but be careful with the numbers. I mean, of course, you will take some screenshots and try to use these maybe in own presentations. But as we always say, don't believe in those numbers that you have not falsified yourself. So when you develop like activities on a professional side these days, you should better take the sustainability goals of the United Nations into account. So, and we're as we're in these presentations, we're addressing quite a number of them. So I said like quality education is one of the really basics that I'm finding here at university. But of course, we have the link to the industry, talking about sustainable cities and communities, climate action, and last but not least, then affordable and clean energy. Yeah. So, and this will also be my first part here. That's something that is maybe sometimes a bit out of the focus is the efficiency. So just to get into the topic, like with two facts from nowadays, what you see here is actually the trend in the last years of the total energy supplied and the energy consumed. And you see there's a huge gap, and this gap is even getting bigger and bigger. So what is this gap about? There's about 1/3 of losses on the way from the primary to the consumer, from the primary energy to the consumer. So there's a huge bunch like to do and tasks to be fulfilled for us. And this is a bit to drive your attention to this point. And on the other hand, we have to ask, like, what is the energy actually used for? Like, we're driving a lot of innovation and like inventing super sophisticated methods. And at the end of the day, 30% of the energy is just like for low enthalpy heating. So these are like points that I'm just to start out with to motivate actually to have a bit deeper look into this. So with this background, everyone is talking about like the hydrogen economy. Billions are spent from the state to foster this development. And the question is hydrogen economy the solution of our energy demand? So having this in mind. In the first place, it looks very promising. So hydrogen has the highest calorific value, specific calorific value in terms of joules per kilogram, and the combustion of hydrogen is free of CO2 emissions, so best choice. If we take a little closer look into the energy density, we see okay. If you compare the mass-related calorific value, you're right. There's nothing better than hydrogen. But now comes the high-pressure experts and say, okay, what do we have to do to get a kilo of hydrogen? And at the end, we have to provide volumes to store our chemical engine energy. And yeah, in the next talk, you will see what it means to store like volumetric or pressure energy in vessels, and it's all about volumes. So if you look into this picture in terms of volume-related calorific value, it's getting different. So the hydrogen at atmospheric pressure has nothing actually, And when you pressurize it to 100 bars, which could be, let's say, a storage pressure in salt caverns, in some of them at least, you're still at less than 1/3 of the value that you can obtain with a natural gas, which is now currently applied. So yeah, having this in mind, you can do a little bit of calculations and look into these the statistical numbers and all of these people that are talking about electrolysis and renewable energies and like all of the hydrogen that we want to produce and also to consume. And currently, yeah, I mean, these are only numbers now, but it's good to see like the relations. The current production of hydrogen, which is basically like for fertilizers and a little bit of energy and is about 120 megatons per year. And the electrical energy required by electrolysis is 4,800 terawatt hours. So you have to get a bit used to these numbers because these numbers will follow you in the next years and decades. The newspapers will be full of them, and you should try not to be misled. And then we come as the chemical engineer, we say, like, what is the efficiency actually of all these processes? Okay, we don't care about efficiencies because at the end of the day we say, okay, we use solar energy, so why do you care about the efficiency? But it's still, you know, this is like in our genes to say an electrolysis in the best of the case, it would work at 70% of the energy would be transformed into this chemical energy. And currently, the electrical energy supplied from solar and wind is about 2,500 terawatt hours per year. So just as a starting point, let's say. But of course, we want to get to the hydrogen economy, and there we need a little more of like perspectives or outlook. And the International Energy Agency gives this type of outlook. So they divide it in different scenarios. You know? So they say there's a scenario that is like to go as is, which is the step scenario, and then you can have like a improvement in terms of an own let's say when it's not compulsory, it's like the industry says, okay, we will try, which is the yellow one. And the non-zero emissions scenario, which is the green one. And currently, we are here in this 2020, or like more or less, with the 25% of solar and offshore production of the entire energy production. And when you take these 25% and take these 25 from these 22,000, then you come up with 20,000. What is it? It should be something like this. 20,000. 1/4, and in general it should be now that I'm thinking it's like it should be 5,000. Well, anyway, you see, don't believe these numbers. It's just like it's just numbers at the moment. But now the perspective is in 2050, in the best of the cases, there's 42,000 terawatt hours by solar and wind. And already a 75 or 76% of this would be for just consumption for hydrogen. And the question is, what are we doing with this hydrogen? So there's not much left to do anything else. And this hydrogen, these 800 megatons of hydrogen there, the perspective is like there's a rising portion of fertilizers, of course, because of the growing population, a huge amount for fuels, and a intensely growing amount also for steel production. That's about like what it's about. But yeah, so we have this hydrogen now, and now we have to, so we have this power to gas. We created chemical engineering, chemical energy. As I said, we have around 4,800 terawatt hours of hydrogen calorific value, which we needed about the same amount to produce. But now we have to like transform it again back to power. And then, yeah, what do we have there? Like fuel cells, combined localized energy plant or power plants, or the electrical vehicle with its efficiencies. And here just some numbers that are also interesting to have, because yeah, and the electrical vehicle will needs like 15 kilowatt hours per 100 kilometers. And yeah, at the end of the day, you can store maybe 4, maybe 6 kilograms of hydrogen in such a tank at very high pressures, up to 350, or in a individual vehicle, then maybe 700 bars. But the refueling technology is also like it's all like a topic on its own, which would like fill in an own presentation actually. So at the end of the day, we call it round trip efficiency is maximum 30%. So we're actually like this whole hydrogen economy is in terms of energy efficiency, it's just like a dissipation technology. So as long as everything is driven by solar and wind, we're okay. But then we have to look into these numbers and see, yeah, what is really the proportion of solar and wind that is at the end of the day that will be supplied. So yeah, but that is not the only thing. So for this hydrogen, it has to be stored, and then like we come as from the high pressure chemical engineering and say, yeah, what pressure do you want? Like how and where will we put it? Like where are we going to place 50 million tons of pure hydrogen? Are indeed can be stored currently, like theoretically, and when you take all the caverns in Germany, put them together, and only place hydrogen in there. But this is technically speaking not possible. And there is like me as a chemical engineering, I'm learning a lot from these geologists and from the reservoir engineers about where can we store the hydrogen. And on their side, the hydrogen for them, or this pressure is not like difficult to imagine. What is going to happen with this hydrogen? What is the solubilities? How is it going to diffuse? There's a lot of like questions that are open and that are still to be addressed. So if we solved all of this, as I said, hydrogen is diffusing. It's a small molecule, and we know this from CO2 or from our natural sources about gases, how they behave, how they absorb, how they diffuse. And there will be hydrogen diffusing to the atmosphere because there's no such thing as an absolute tight reservoir or plugs. And then comes the point: hydrogen is not climate neutral, so it does something. There's reactions going on, or there's also like it's working as a scavenger, or reactions going on. There's natural gas that is not being that is not reacting then in the atmosphere when there's also hydrogen. And so there is it's if you look into it really like from a scientific point of view and really facts-based, you have to say that not even hydrogen is climate neutral. So I'm not saying that hydrogen should not be part of the solution, but like we have to look at it like from a facts-based perspective, and I think like and my intention is actually to give you some numbers to start looking into these processes. Next point is the circular economy. So the circular economy, as we saw with hydrogen, doesn't really entirely work out. So let's see what happens to the polymers. In all these processes, also talking about hydrogen, we need new materials that sustain these high pressures of hydrogen. We have problems with the corrosion in steels, embrittlement, and these things. And there are some new polymers coming up that are really a grand advancement. So and they are the demand is that they should sustain high temperatures, high pressures. They should have lightweight, chemical resistance. So all fine, and we're like on a really good way. But there are also new challenges coming up for recycling. So we're just now discussing recycling of the old known polyolefins and the common stuff. And now we already have to talk about like what is going to happen with all these new materials. We have to look into the second life already during product design. And we have to think of not always downcycling, not only using the old polymers for wastewater pipes and so on. So these high performance polymers, you use them in H2 tanks and pipelines, batteries, sorry for the typo here, and photovoltaic applications, aeronautics, of course, membranes, wind turbines, geothermal wells, so and so on. This is just an example of one of the materials that is now being like re-innovated, let's say, a so-called flexible pipe that is built of a lot of layers, and these flexible pipes, they're used in lengths of kilometers in the subsea for producing oil and gas, but in future also for carbon capture and storage. And you see here the polymer liner is the essential part that or the barrier that keeps the gas and the oil inside, or the fluid or whatever you have inside this pipe, while you have a lot of steel tensile wires and collapse carcasses and everything that make this pipe like super heavy and very expensive, and also failure sensitive. So the new solution is to have fiber reinforced polymers with only one single layer, and they're pressure resistant, corrosion resistant, and everything. So, but there comes the problem. So how do we recycle these polymer composites? So for recycling, we have basically like these 5 options. Landfilling would be the simplest. So you just mill it and then grind it, and then you just mix it with some other stuff for making streets or houses. Then incineration, which is now commonly called thermal recycling, which is technically simple, but you have these emissions, loss of material. This is a no-go in future. Okay, the pyrolysis, there are some new technologies that even you can recover the fibers, and you have you produce a source actually for new materials, but it has a high energy demand, and you have a lot of emissions. There's mechanical recycling, which is basically goes direction downgrading, and the chemical recycling, which is, I would say, one of the most promising methods for recovery of the polymers and the fibers, but everything has a but. There are solvents required, and still it's on a pretty low technical readiness level. So, but if we look into this, maybe we as chemical engineers can add some value to it. So the recycling in principle would then the chemical recycling would work through sulfolysis, And somehow you have to separate then the polymer and the fibers and try. At the moment, the fibers are very valuable and they're very high price products. So we come here as engineers, as chemical engineers, we have to find a smart combination of these processes. But since we are able to think in analogies and synergies, we may be able to come up with a solution. And we have to think of a market for a new product. And also, I'm talking here to, or you are talking here to specialists in this area, which I'm not a specialist in, but we will listen to some talk later about this new type of materials. So coming to my last point, actually, the education. So nothing in innovation and development will happen if we don't have skilled personnel. So there's really a demand for knowledgeable, critical, and creative brains. And this is what I was finding. I mean, I was working in industry before, and I came back to university here 3 years ago, and I'm seeing how this development goes. And I mean, the lack starts already at school, but it continues at university, especially the point of critical and creative brains. So if you have, if you're looking into just like learning and focusing on your exam, then you may not have time to really think of some innovations. Of course, you need fundamentals in thermodynamics. You need to learn about the energy and mass balances, as I said, and you need a global view. And this is what I tried to point out with this hydrogen example. So here at university, we invented a new bachelor course. It's called Geoenergy Systems, which I also call the Fridays for Future course. But unfortunately, I haven't met any one of those here so far. But still, we're not giving up. And these are like, we're trying to combine like the geo-based energy approaches that I maybe showed you a little bit with technologies of sector coupling. And this is exactly where we as chemical engineers can step in. Circular economy, of course, should be actually common sense and knowledge transfer. Just as an example, at the beginning, I pointed out that 30% of the consumed energy actually is for heating at low to moderate temperatures. So why should we combust high valuable natural gas to heat our houses if we only actually need like 30 or 40 degrees? So at the moment, the heating or like the heating demand, these 30% of like lower than 90 degrees is covered by oil and gas. And and even at the moment, what we call Fernwärme, the long distance heatings, is more than half of fossil fuels. So there's only like a little portion of renewables that is really implemented here. So what these students have to learn is, as I said, like the thermodynamic fundamentals, and low temperature is high exergy. And what is exergy? But I think I would like to leave you with this question, and just finish saying, yeah, what are the challenges for our future education? Because we're focusing simplified concepts that are offered by the media and politics, and we have to give answers. We have to give answers like maintaining the objective standard here, supporting to broaden the perspectives, to incentivate and generate the conscience for the consequences of what we're doing and what mankind is doing actually. But we shouldn't also leave out of our focus generating the curiosity and the fun, which is, in my opinion, is getting lost. So technology is increasingly becoming the bad boy as such. So because there's always some sort of consequence of what you're doing. So our challenge is, just to sum up, and getting back to the very first slide, is to make use of the energy saving as an energy source. And this is also to create a conscience for this, to apply the energy and mass balance on a global scale in the right way, to minimize the exergy losses and to provide high quality education, which is the sustainability goal number 4. So yeah, I want to thank you for your attention and for listening, and I'm open to questions.
Philip, thank you very much for this very interesting lecture and also all questions that you raised. So I would like to check with Martine if there are some questions in Q&A, because it seems that I cannot enter them. At the moment, I see no questions.
No question for the moment.
No questions. So please, if anyone has any question, write it in chat.
Also, you have my email here, so I'm happy also to be contacted.
Okay, then Philip, thank you very much for your talk.
Yeah.
Okay, we continue with the second talk that comes from Uhde, High Pressure Technologies, a company that delivers solutions to chemical, material, automotive, pharmaceutical, and food industries with pressures of up to 14,000 bars. Today with us are Dr. Judith Kremer, the specialist in supercritical fluid technologies and head of sales of the supercritical fluid department, and Dr. Jasna Ivanovic, specialist in high pressure processing applications and quality management, and part of the group of high pressure processing. Judith and Jasna, welcome, and the screen is yours.
Okay, thank you very much. Thank you very much. We will start now with the presentation. I think we both just, I don't know if you see my screen and what screen you are seeing at the moment.
Yes, first screen.
Okay, good. We are very pleased for invitation to be here with all the fellowship we have in today's session. We want to take also audience that are joining us together. My question and our question and all is, have you ever been asked to justify sustainability of your activities and to define the sustainability, to evaluate sustainability of your activities at your university for your research or your business in your company? If not, I guess you will be soon faced to this challenge. And today, my colleague Judith Kremer and myself, Jasna Ivanovic, want to shed a light actually on how Uhde sees sustainability and how Uhde drives sustainability at different life stages of high pressure units. Uhde is, let's say, more than 100 years old company, and it is a subsidiary of ThyssenKrupp Group for more than 30 years now. It specializes in high pressure components and equipment for the high pressure applications up to the 4000 megapascal, and also in build up of the pressure of the whole plants, turnkey solutions for the high pressure applications. What Uhde is trying, and what is the Uhde mission is to improve sustainability in all the phases, starting from design and manufacturing to use and service of high pressure equipment, but also in the last stage, and that is the post-use of components and high pressure units. Creating a sustainable products means using sustainable processes that are minimizing negative environmental impacts, conserve the energy and natural resources like water and gases that are safe for the employees, communities, consumers, and at the end of the day that are economically sound. Our today's example of Uhde activities actually are intended to tackle some of the metric categories within all three aspects: environmental, economical, and social aspects of sustainability and sustainable manufacturing at different stages of the life cycle of high pressure units. Just before we go on to that, in a nutshell, what are our products for the high pressure processes? Starting from the lowest pressure, we produce the lowest pressure applications. We produce the valves and pipelines for the chemical industry, fertilizer units, urea units, then further on autoclaves and pipeline reactors, heat exchangers, high pressure pumps also for the chemical industry, LDP plants. That is very well established part of our business. For the high pressure, we build up also the high pressure equipment like high pressure pumps for water jet cutting, which are used in a variety of the sectors, from material industry, automotive industry to food industry, for example, to remove the bones from the fish fillets in a very short time. Today, our examples, as I say, will refer to our turnkey solutions, and those are lab plant and industrial scale units for high pressure processing using the supercritical fluids up to the pressure of 100 megapascal. And those are used in pharmaceutical, food, material sector. And beside that, we also build up key-turn solutions for the pasteurization, for the cold preservation of the food by using the high hydrostatic pressure. And today we are going to also speak about so-called high pressure processing units. Besides, Uhde is also offering different services which are related to the high pressure equipment in the units, starting from installation, inspection, maintenance, and training of the users of the high pressure equipment, and also different services like contract services and support by like HPP tolling service. Today we will also mention this in relation to the sustainability. And also we support our customers in exploring a new application of our equipment. I would like to start today with the HPP process and HPP unit. HPP process is in-pack batch method for non-thermal preservation of packed and chilled food. Also intermediate food products or ingredients for the food industry, lately also for the pharmaceutical industry. The products are transported into the process baskets, within the process basket into the high pressure vessel, which is filled with tap water, and further on water is used as to transfer the pressure to the product and to build up the pressure by using external intensifiers, and the product is exposed from couple seconds to couple minutes to an extreme pressure to achieve different effects, normally inactivation of the pathogen and spoilage microorganisms, but there are also other applications. And after that, product is ready for the next step or the final use. It is a stand-alone unit, and it can be also combined with other units for the filling, labeling, sealing, and so on. Production of HP units dates from late 90s, starting with production of pressure assisted thermal sterilization, so-called PATS units, with a horizontal high pressure vessel and an internal intensifier, which are combining simultaneously pressure and temperature to achieve, for example, sterilization effects in a very short time. These units are today also produced, and they are mostly used at universities and institutes for research and consulting activities. 10 years after starting production of PATS units, company used accumulated know-how and in building of high-pressure vessels and equipment like high-pressure pumps, as well the other resources in the house to build up standard HP units for industrial use. And today they are sold in various sizes worldwide, from Oceania, Asia, Europe, and USA. The first concerns about sustainability start in design and manufacturing phase. Namely, all the core components of the high-pressure units, like a high-pressure vessel, high-pressure yoke, that is this dark blue frame, which practically absorbs the axial forces during the pressurization of vessel, pipeline, and the component of the external intensifiers, which are intended to build pressure in a very short time, are exposed to very extreme pressures and high-pressure corrosive fluids like tap water. In order to reduce material use, to reduce the costs for the spare parts, and to prolong the lifespan of the equipment, because it is pretty costly equipment, and also to ensure the safety of the employees, operators, a certain concerns has to be taken up front regarding the design of these components. So basically, what we use is anti-corrosive high-strength materials for all the surfaces that are coming into direct contact with the pressure and the water. And to increase the fatigue life of the components which are coming into contact with the high pressure, we use in-house pre-stressing techniques such as auto-fretage and wire winding to introduce beneficial residual material stress by control plastic deformation with ultra high pressure, with hydraulic fluids or the mechanically, in order to eliminate fatigue cracks in the wall of these components. With that, we practically hardening the walls and ensure their long-lasting use in practice, because these units are used under the pressure in a cyclic regime, pressurization, depressurization many times a day, and that requires a special design precautions. We also use for the multiple life cycle of the units, we also apply 6R approach. So a lot of units are used multiple times. They are remanufactured, they are redesigned for either different product, different application, or we have examples of just remanufacturing PATS units to the standard HPP units and so on. And at the end, we also use a redundant safety system measuring pressure inline in the pipelines on the both sides of the pressure vessel, and also the extension of the vessel in axial direction from the bottom and top to ensure safety of the unit and of the operator. For example, for the example, we use for the pre-stressing of the high pressure vessel, which is intended to be used at the pressures above 1000 megapascal. We use wire winding technology to pre-stress this vessel, and we use around 230 kilometers of wire for that person. The same methodology is used also for the yoke, for the frame. It's not only design, but also use of the units can decrease not only operative costs and investment. It can also it is possible also to decrease CO2 footprint and energy consumption by smart use of these units. For example, by choosing the right geometry and size, as well as the type of the packaging, we can also influence the energy consumption per kilo or the liter of the product by increasing the filling rate of the high pressure vessel with the product. And by using a bulk packaging like bags or kegs, for example, to produce juice, we can also decrease the use of the packaging material, which can be correlated, for example, with CO2 equivalents. This is just an example for comparison. If you use kegs instead of the small smoothie bottles of 250 to 500 milliliters, we can achieve three times less PET use, 4 times less energy consumption per liter of juice, and up to 3 times less CO2 footprint. Also, HP units are used for the sustainable food production commercially, for the shelf life extension, safety, efficiency, upcycling, and added value. And all these applications can contribute to sustainability in all 3 aspects: economical, social, and environmental. For example, by extending shelf life of extension, we can decrease the food wastage, overprocessing of food, saving of the resources like water and the land, and we can also improve the local economy because the small producers, the local producers can also sell their products also to distant. They can place their products on the distant markets and profit from it. Increasing the safety of the products is very important for improving the public health and the environment, and has positive effect on the environment because of less meat to be disposed, and this can be also correlated with CO2 footprint. Efficiency, HPP can be used also to open the seafood without using a knife, without contamination and discard of the product. It can be used to get a product with a high quality, higher price, and it improves also the well-being and safety of the employees. Very popular, Professor Aga said, a circular economy. Also with HP, we can contribute to that with using the discarded vegetables to produce the high added value products like smoothies and profit of it, with saving the resources at the same time. Thermostable bioactive components, also like a polystatine, which is found in the fresh egg yolk, can be also preserved by high pressure process, which is used to eliminate salmonella. Further on, the product is pulverized and polystatine rich product is used for the supplement mixtures. Also, other plant bioactive components can be concentrated and safe in food. So it is good for the well-being of society. This is just for illustration what kind of numbers can be used to correlate the influence of the process to the CO2 footprint and energy saving per kilo or liter product. Also transport costs. Here you see the shelf life extension can be from couple days to 1 week or couple weeks up to couple months extended, which helps to, of course, save a lot of the transport costs, save a lot, reduce the overproducing of the food, and yeah, which is also helpful for the environment. Efficiency, also this the yield of the product, the hygiene of the product, quality of product also can be related to the some metric units like financial units like profit or also savings of the food and resources to produce the seafood. And of course, the contamination of meat with HPP saves a lot of meat, which would be normally discarded because of the normal pathogen spoilage. Among the applications, the fast-growing market for the HPP are definitely meat sector, juice sector, and vegetable sector. But in the last 10 years, HPP service and contract service for the treatment of the different food is also a very well established method to support the local producers that are not that don't have budget to buy the machine, to use and benefit of HPP methodology. That's why we also opened our HPP center in Germany to support the local economy, but it is with offering the machine for the local industry. But it's not the only sustainability aspect that is covered by this. We also use this center to improve our equipment, to optimize production process, to test new components in the real industrial environment, and also to explore new application with our partners in pressure, and that's our customers, DL as a strategic partner, different universities, and professors and students, and we also look forward to see you in our HPP family. So thank you. I will just, it's a little bit short time, so I will just give a stage to my colleague Judith and then look forward to the questions.
Okay, yeah, thank you very much, Jasna. So now we will switch the topic to the supercritical fluid extraction. First, let me say welcome also from my side. It's a pleasure to talk to you today, and thank you for inviting us to speak. As an introduction, I will just shortly or briefly summarize the CO2 extraction process again, which is mainly divided into three parts, being the extraction part, the recovery or supply part, and the separation part. So heart of the extraction unit are the extractors, in which the raw material, mostly solid material, is placed by using insert baskets or extraction baskets. Then the extractor is closed and the process of extraction can start. For starting the process, liquid CO2 coming from the CO2 storage tank or buffer tank is first subcooled, then pumped to extraction pressure and heated to extraction temperature before it is fed into the extractors. In this moment, the CO2 is in its supercritical state, meaning it has both properties of a liquid and a gas, which means that it has a good solvent power for natural extract, but the CO2 can also easily diffuse into the porous matrix of a natural raw material, dissolving the extract or targeted compounds when it is leaving the extractor, and then it's routed to the separation part. In the separation part, CO2 and extract are separated only by changing pressure and temperature. And as you can see here, you can also achieve a fractionated separation by using separators working at different pressure levels. After the last separator, the CO2 is not discharged to the environment, but it's recondensed by a condenser and fed into the buffer tank again, where it can be used for the process. In industrial system, an industrial sized system could look like this, for example. So this is an actual plant we built a few years ago. It's an example for the extraction of algae, meaning you see two extractors here, the light blue ones on the middle left side. Then you have two separators which are on the upper right hand side, also in light blue, and you can see that it's kind of a modular system, meaning it's completely installed at our site in Hagen, then just disconnected at some points shipped to the client, and it's mechanically and electrically installed in a short time period before it is up and running with the client. So this one was for LJ extraction, therefore it has a high design pressure of 1100 bar, only 2 extractors, 2 separators, also one operating at a quite high pressure, 200-300 bar, one operating around 60 bar, then the CO2 pump required for the process, the buffer tank, heat exchangers, valve, instrumentation and everything. So the footprint of the whole system is quite compact. It's roughly 9 to 6 times 6 meters. So it's one of the smaller systems, I would say. Okay, thank you. So this type of supercritical fluid extraction process and unit is used in a lot of markets. So I brought just a short overview of supercritical fluid markets and applications. I just want to highlight some of them because it's only an overview and not all processes and products are listed here. So we have for the food and beverage sector, for example, the natural flavor and fragrance extraction, food supplements is a big part, or the removal of pesticides, for example. Then we have the cosmetic industry with the natural fragrance extraction. For example, the pharmaceutical industry is highly interested in active ingredients, for example, cannabinoids from hemp. But also supercritical CO2 is used for particle or crystal engineering in pharmaceutical applications as a high pressure spraying process, but also it can be used for sterilization or decontamination. I think in another talk you will hear more about special materials which can also be produced during supercritical CO2 when you are looking at the aerogels, but you can also use CO2 for impregnation on coating, and so on and so on. There are a lot of more. But why are there so many applications? That is because supercritical CO2 provides, I would say, unique advantages when used as a solvent. So you have a quite gentle treatment of the product because you have low process temperatures, around 40, 50 degrees for most of the applications. You do not have the need to process your product with organic solvents like hexane or something like this, which could leave residues in your product or which must be separated with quite an effort from your product after extraction. You have an easy separation and only a few process steps when you use the CO2 extraction, so it's quite an easy process, as I already established. And furthermore, CO2 is non-toxic and environmentally friendly. Therefore, it is usually considered as a green solvent. But with the decreasing demand regarding sustainability, I would like to have a closer look if we can make the process of CO2 extraction not even a bit more sustainable than it is right now. For example, we have a kind of loss when we depressurize extractors after the extraction to atmospheric pressure. There is a bit of CO2 which we lose in smaller systems or in industrial systems. So again, coming back to the process flow sheet from before, so I'm talking about the highlighted area in orange here, the recovery or supply part. And we usually use or reuse the CO2 during depressurization of the extractors down to a pressure around buffer tank pressure. It's around 60, 70 bar or something like this. So this from extraction pressure to the 60 bar, this one is recovered, but the rest is discharged to atmosphere, for example, in the smaller systems, in a lot of the systems. This is fine for smaller systems, but if you look on the industrial side, for example, a hops extraction plant, which has several extractors with a volume, a net volume of approximately 4 cubic meters, so these really large vessels. And there, if we, with every cycle, we lose CO2 from 60 bar to atmospheric pressure, this gives us kind of a large CO2 loss. So with the normal CO2 recirculation from low pressure separator to the buffer tank by just condensing it, you can reuse approximately 72% of the CO2, which is inside the vessel during extraction. If you add a one-stage recovery system, which then consists of some vessels and a compressor or just a compressor, you can recover approximately 91%. So approximately 20% more of the CO2, which is inside the vessel. And when you even add another stage, so a two-stage, for example, if you add another balloon to the system, you can recover more than 99% of the CO2, which is in the vessel during extraction. Of course, you have further losses in your process, meaning you will have some losses during venting, cleaning, or other, depending on pressure, temperature, times, which are not considered in my kind of small example calculation here. But what you have to keep in mind is, of course, we recover more CO2, which is a good thing, I would say, but we also need to we have a high power consumption because we have more equipment, meaning we have more investment costs up front, and also we will have a higher energy consumption because we have to have the compressors running, and also we have to add some coolers to the compressors so our CO2 would not get too hot for the process. Therefore, it's always a bit of a trade-off what you would like to do, and it's really worth it to calculate it if the CO2 recovery and also what kind of CO2 recovery is the best solution for your specific system. Another example for sustainability, and I have to admit this is my favorite example from one of our extraction plants, is the reuse of a plant, one of the parts of the 6 Rs Jasna mentioned before. So the plant you can see on this picture was built, I think it was in the early 1990s for the decaffeination of tea, and it was running for 15 or 20 years when the customer decided he wanted to shut down the decaffeination of tea operation, and he sold the plant. So we relocated this plant to Germany then, and in 2010, and since then it is running for extraction of hops. So it's running now for more than 30 years, and yeah, maybe you already drank some beer with hop extract from this kind of system. So it's also a possibility because these systems are mechanically very stable and can run for 30-40 years. It could be an option to repurpose a used system for a new application, for example. And even if the mechanic is still, the mechanic system is still valid, and you say, okay, but the instrumentation is outdated, it's really no problem. So we do a lot of control system and instrumentation revamps for our plants, for example, after 15 years or something like this. So it's really possible. And therefore, we try to increase sustainability of our systems. Okay, now I'm at the end of my presentation. Thank you very much for listening, and I'm looking forward to your questions. Or we are looking forward.
Jasna and Judith, many thanks for this extensive information that you presented. We have 2 questions. First question for Jasna is it possible to send references of the results of the carbon footprint presented? They look interesting, but I have some doubts.
Yeah, it is possible. Yeah, it is possible. These are public, basically, data which are used. Some from the Austrian Institute. They calculated CO2 equivalents for the production of the 1 kilo of PET, and we combine it with our information on the filling rate, and yeah, it is possible to send it. So there, just I don't know. My email was on the last slide, but it can be found on the internet site, so they can send us a request.
Okay, thank you very much. The next question is, what properties define the shelf life extension, and why there are such big differences between them, like such a milk and baby food?
Yeah, of course. There are two things. There are various things that various let's say parameters that are defining the shelf life. Those are just not only microbiological, but also the chemical and sensorial parameters. And the differences is that not only the HPP parameters, but also the product parameters like pH value, like ingredients of the food, like water activity, influence the effects of HPP on shelf life. So sometimes, for example, for the products such as juices with a relatively low pH value, we have very excellent results when it comes to extension of the shelf life. But on the other side, when we are having a nutritious products like milk, we have maybe extension of shelf life a couple times only. On the other side, we also have very sensitive products like maybe fitness muesli, the ready-to-eat meals, which consist of many components. So the cross-contamination occurs in a day. And with the HPP, we can basically eliminate all the spoilage microorganisms and increase the shelf life 30 times. So it's not only microbiology, it's also the enzymatic activity that influences the appearance and of the products, and also the shelf life of the products. And with sometimes some enzymes are more, and sometimes some enzymes are more, and sometimes some enzymes are less resistant to the high pressure. So it's a very complex topic, and the effects are practically product specific, but we try to generalize it for the product groups.
Thank you very much. We don't have more questions, so all participants may write to Jasna and Judith connected to this extensive information that they presented. So thank you very much for participating in this Spotlight Talks. Now we will go to the third talk with Dr. Jean-Yves Clavier about scaling up of supercritical fluid technology and an example of process industrialization. So, thank you. Okay, we just don't hear you. You are muted. Yes, super.
Sorry, thank you, Irena, for the introduction. Thanks for the invitation. And thanks everybody for being here. So my presentation will be a bit more focused compared to the last one. It will be a little bit the continuation of Judith's presentation on supercritical fluid technology. I will also talk of the industrialization of this technology. And as we are in a chemical engineer discussion, I will try to show how chemical engineers could help making this technology a little bit more sustainable with the example of some continuous process. Just a quick introduction about myself. I've been working for quite a long time now in supercritical fluids, a bit more than 30 years. I've been working in a French company called Sephorex for doing chemical engineering for process development and high pressure equipment manufacturing. And we were seeing a lot of research development at that time and not so many industrial application. And in 2016, I decided to try to help this industrialization, to focus all my time on still providing some chemical engineering service for process development and supercritical fluid equipment design, but focused on industrialization and just proposing engineering service as an independent engineer. My talk today will have three parts. First, a very brief introduction, as Judith already nicely presented it, about the opportunities and challenges of this technology. Second part will be on solid extraction to show how chemical engineering can help making it a little bit more sustainable. And the main part will be focused on continuous processes. So I will not what Judith said about the opportunities. When we speak about supercritical fluid, this is actually mainly CO2. And why CO2? It's just because it is cheap, harmless. It can be used at relatively cheap, relatively low temperature, and it could replace organic solvents. Another great advantage is that you can process materials and collect these materials or these extracts without residual solvent. And when you see the motivations of using CO2 as a solvent, this argument is very strong, because when you look at the industrial applications, the regulatory reasons are often the main one to use CO2, because you get no residual solvent, you don't use any other solvent. A second motivation is sometimes related to the quality of the product, because we can process at relatively low temperature and we can get some selective products playing on pressure and temperature. And again, when we look at the motivation, I have to admit that most of the time the marketing aspects is often decisive in the decision to invest, because supercritical fluid technology is really presented as a green technology. Actually, it's not a green technology by itself. It is still submitted to the thermodynamic, and it is up to us chemical engineers to really make it a little bit greener. So this is what I will try to show. I will not spend time here on the CO2 cycle. Judith already explained it. So we are working at above critical point at relatively high pressure and temperature. And as Judith explained, we have a continuous cycle of CO2 playing with temperatures and pressures. So we go in gas phase to collect the products as they are not soluble anymore. And then we have a CO2 cycle that is usually composed of a condensation of gas CO2, a compression with a pump, and a heating to go back to the supercritical area. When now, after speaking of the opportunities, when you look at the challenges, we have quite a lot of limitation that we have to deal with. So technology is a high pressure technology. So Uhde is quite an expert, and we had a nice demonstration, but still we have to face with the cost of the technology, even if, as Judith showed, it is a long-lasting system. We can use it for tens and several tens of years. We also see some systems that are 40 years old that are still working very nicely. So we have to take that into account when we try to convince customers to use this technology. And we also have to admit that when we use flammable solvent, it is also costly. So we have to deal with the cost. And actually, we use CO2, as I said, but one limitation is that we don't have so many choices. So using CO2 induce limited range of application, because CO2 is a very porous solvent, and we usually have to face with very limited solubilities of our product. So sometimes it's an advantage when CO2 is a good one, but it really restricts the number of potentially economical application. But well, we have to face that. We cannot play with this as engineers. The 2 points that we can play with are try to understand and optimize the energy management, because as I said, as CO2 has really low solubility for the product, it brings high recycling cost in the CO2 recycling, because we use used quantities of CO2. So we have to optimize this. And when we look at other fluids, we use also water, pressurized water, not in supercritical, but heated pressurized water for extraction. And again, here we have quite high energy requirements compared to solvent requirements. So we have to optimize for the best this energy. The second point that we can optimize, and Judith also mentioned that, is we have significant amount of waste of CO2 when we depressurize the vessels and when we collect the products at atmospheric pressure. So we have to minimize this waste that have a significant carbon footprint impact. So we have to optimize depressurization procedures and collecting procedures for the products. When we look at solid extraction, which is the main extraction, it's more than 90% of the application of supercritical fluids. The main application are in the cosmetic domain, in the aroma domain, in the ingredients, high-cost ingredients domain, and we see now a little bit more, but again, more than 90% of these applications are in these fields. And we have to admit it's because of the high cost of the products. And I'm sorry to observe that, but in these industries, even if people show that they are concerned about sustainability, when we look at the condition, it's not always done in the best conditions, and it leads usually to a relatively high cost and significant carbon footprint impacts. So if we want to widen the scope and the range of application of this technology, we really have to work on the sustainability. So I would like to speak a little bit more of two potential range of applications for the low value products, like the natural waste valorization in the circular economy domain, or the plastic recycling. And these are really two fields where we see interesting developments. So let's try to see what are the consequences for the optimization and for the chemical engineers. We have to use the system as good as possible. So usually we try to make it as continuous as possible for the CO2 loop. We try to pump continuously. And this is why, as Judith showed, we use several extractors. We have one that is continuously extracting and the other one that is used for this sophisticated depressurization procedure for changing the product. So we can use at least 2 vessels or even more, 3 or more, when we have long extraction and when we have extraction that are depending on the diffusion. We have to have a long contact time, and we use more extractors to have a kind of carousel operation. When we look at the extraction curves, when you look extraction yields compared to the amount of solvent that is used, we usually have this type of curves with a relatively quick extraction at the beginning and the long extraction at the end. This is what is always observed in natural products. And usually we have a first step that is quite efficient, where you are limited by the thermodynamic and the solubility, and then a second phase that is much longer. So you have to find an optimum between the efficiency and the amount of CO2 that is used. And this is the role of chemical engineering, to try to optimize this, to have first an idea of what is thermodynamic limitation, diffusion limitation, and hydrodynamic limitation. And this is really standard chemical engineering work what is a bit specific to this high pressure technology is that we have to use specific tools and specific methodology to estimate all this. The curve as was showing was related to the extraction of the plastic waste, where we extract the plasticizer, again in a context of circular economy. And my role as a chemical engineer is to optimize all this, because you see that it leads to huge quantities of CO2 if we want to reduce the amount of extract. So the objective of the optimization work is to try to model this to reduce and to optimize the extraction. So we try to estimate thermodynamics, diffusion, hydrodynamics. For solubility measurements, for instance, we use this kind of sapphire lab system. You see one example here. And we place the extract, the pure extract in the cells. We have a little flow of CO2 that we try to saturate, optimizing the contact. And what is going out allows us to determine the solubility of the extract in CO2. And the good point about this technology is that we can play easily with temperature, with pressure. And this is a very good example, this application of extraction of plasticizer from a plastic, as we have very, very good solubility, which is quite an exception, but we have to take this opportunity, and we can reach, optimizing the thermodynamic, we can reach some domain here above 400 bar, where we have a full solubility. We are actually in what could be called the supercritical state of the mixture, because whatever is the amount of extract that we put in the cell, if we pressurize it to these conditions, we have only one phase. So we can say that we don't have any thermodynamic limitation. We don't have any solubility limitation for this extraction. So this is a very nice extraction, and there is, from my point of view, a great potential for this recycling of plastic. And with some other methodology, like the one we use in chemical engineering, we can do some residence time analysis for the extractor to try to estimate what could be the remixing, because this is one of the challenge here. We want to go to very low residual content of the pollutants and of the plasticizers. So we have to optimize hydrodynamics, and the main limiting factor is diffusion. So we can again model this to understand everything, and with a couple of simulation and a couple of additional experiments, we could reduce the original curves that we obtain at lab scale to much more interesting condition when we reduce the amount of solvent by a factor of 10, going from 50 to almost 5. So again, we have what is already used in all the production equipment, this carousel operation mode, but optimizing and understanding this application allowed us to determine what were the requirements in terms of feed preparation to minimize diffusion, also to put some specification to have a good control of the hydrodynamics in our vessels. And as it is very large scale application, like Judith said, we have to maximize CO2 recovery to minimize the impact, repressurizing the vessels in these steps of depressurization to minimize the CO2 that is remaining in the vessel, and also optimize the depressurization of the vessels, because even if you depressurize correctly, CO2 has a great affinity for the plastic, and we have to adapt the depressurization procedure to minimize this amount of CO2 that remains in the plastic. So in order to conclude these first steps related to solid extraction, there is a great work of chemical engineering to optimize the process. But there is also two very important points that we have to manage in any kind of large-scale application. It's optimize the CO2 recycling. So what we talked, both Judith and myself, is a process of CO2 recycling when we pump the CO2 in the liquid state, but in some process at lower pressure, we also have to consider a gas recompression with gas compressor that could be more economical for energy. And we have also other recycling modes, putting an adsorption bed, and instead of depressurizing, cooling and repressurizing, we can actually collect the extract at the same pressure, collecting in an adsorption bed or in an absorption with water. This is, for instance, what has been described in the past on coffee. This is what is done in the dyeing of textile. We have two vessels, one with the dye, one with the vessel, and we are operating in the same pressure. And we should also consider this when we have an extract that can be easily adsorbed. We could think, for instance, of volatile molecules when we try to remove a solvent from a solid, or with some contaminants that are present in very small quantities in a raw material, and that could be catch with adsorbent bed. These are possibilities to consider to minimize the energy requirement in a recycling cycle. There is also some nice development in how to use membrane in the recycling process to, again, to try to collect the extract at the same pressure that the one used in the extraction process, but using selective membranes to avoid this recycling cycle of CO2 with a lot of energy requirement. The second point that we have to play as chemical engineers is to decrease the CO2 consumption. Judith explained it. I already explained it in the previous slide. So for most of the high capacity application, we need to decrease the CO2 consumption, working on the gas recompression and working on the depressurization procedures. There are also other procedures, but I don't have time to detail here, with exchange of solvents. So yes, this is the conclusion of the solid extraction. We have to minimize energy, maximize CO2 recovery, and try to make process as continuous as possible, including the product handling. And of course, use CO2 only where it is good at. And on my side, I'm convinced that there are not so many applications, and we really have to focus where CO2 is good at. What is true for CO2 is also true for other solvents. The solvent I presented is a subcritical water extraction. We use water in a pressurized state to be able to increase solubility in water of less polar compounds. So we use water at 120 degrees up to let's say 200 degrees to modify the solubility of the water. And this opens a range of new application for water, basically comparable to some mixture of an alcohol with water. But again, we are faced with dilution and too high energy requirements compared to this heating of the water. And if we dilute too much, we are just not economical. So again, we try to develop continuous process. And here, as we have lower pressure, the pressure in the subcritical water can be typically between 5 and 20 bar. So it's easy to use extrusion-like extractors where we push the feed with screws. This has both the advantage to have a lower dilution. We can and also to press the cake of solid at the exit of the extruder, and we can therefore minimize the dilution. We obtain factors of dilution about 4 times, and this makes the process much more attractive. Looking at other process than extraction, we will see a little bit more about this continuous process and how this can improve the energy requirement and the sustainability. This is quite a usual idea of chemical engineers. So the topic of this is it possible at high pressure and for supercritical free technology? The first process we can talk is how to process liquid with supercritical fluids. This is much easier as we don't have a solid, we have a liquid, so we can pump it, and we can basically have a contact of a liquid with CO2. We can even contact them concurrently, so we can pump the liquid in a column at one of this level, and we can have two sections below the feed introduction and above the feed introduction to have a key kind of enrichment section and a section at the top, which plays a role like in a distillation as a reflux. So we have one introduction and two exit, an exit at the top for the products that are extracted. This gives a light fraction that is called extract, and we have a heavy fraction that is called raffinate, and we can have very different fraction on these two streams. And we can, of course, imagine to have a reflux of extract that is introduced at the top to increase the selectivity of the process, like in a standard distillation. So this has been developed in the last 30 years. There are not so many applications at large scale. And this can be modeled now quite efficiently. We can represent the column as different theoretical stage, and each stage we can estimate that we have an equilibrium and some mass transfer. So we basically model an equilibrium between the two phases, the heavy phase and the light phases. We add a model of mass transfer, and then adding the diffusion, the hydrodynamic and the thermodynamic, we can have good model for this. And one example that has been developed in the last 20 years is the fractionation of omega-3 ethyl esters to concentrate in heavy omega-3s, the famous APA and DHA. And we have been working a lot on this application to concentrate the omega-3, the most famous one here, maximizing the yield. We obtained very good simulation results and experiments that fits very well with this simulation, but this leads to quite high ratio of CO2 over feed, and this has really a significant cost. And actually, you always need to compare the green aspect of this technology and the economical aspects compared to other technologies. And for this technology, the competitive technology is molecular distillation, where you don't have the CO2. So you just need to evaporate once the oil. You, of course, can manage a reflux too, but we have never been able to make it use at industrial scale because molecular distillation was always much more interesting in terms of energy. So, but this has not been used, but some people show nice columns here of 12 meter, 400 millimeter diameter for some applications that are used in Asia, in India here for purification of capsaicin. So you have nice enrichment factors of again 4 times the initial content in capsaicin in a paper extract. On my side, I'm not convinced that we need such a high column because most of the industrial application of liquid fractionation don't need such selectivities, but this is used at very large scale. The main applications are for aqueous feed fractionation, for instance, for aroma fractionation on distilled or fermented solutions. So aqueous-based solution that can be purified with CO2. You also have organic solution fractionation from lipid to obtain polar lipid, or further steps after solid extraction for essential oil purification, and also some application in purification of polymers. So we are still very optimistic about potential development, but that's not easy to to optimize and to make it economical. Next application that I want to present is chromatography. And the question is still, is going continuous in a chromatography mode interesting? So just a reminder about chromatography. Chromatography is basically a column, a stainless steel column that you fill with a stationary phase that has an affinity for the product. So you have a column here, you inject at one hand a mixture of product to be separated, you push it with what is called the aerient, which is a solvent, a mixture of solvent, here CO2. And as the two products A and B have different affinity for the stationary phase, they progress at a different speed in the column, and at the exit of the column, if you look at what is at the exit versus time, you get first B that is going faster, and then A that is going slowly. Again, you can model this with modeling the axial dispersion in the column, the convection, either the thermodynamic behavior of the partition, and you can represent this peak. As Philip was saying in introduction, I just added this slide when he was talking. We are chemical engineers, and we never forget the second principle of thermodynamic. And SFC is often presented as a green chromatography without solvent. So if it was true, you get a mixture here of A and B, and this is marvelous, you get A and B separated. That would mean that entropy change is negative. So is it the case for SFC? Obviously not. We don't forget the second principle of thermodynamic, because basically chromatography, the cost for this, the entropy cost for this is dilution. And chromatography is terrific regarding dilution. It is a very dilutive process. This is why, before going to continuous, if we look why CO2 can be interesting for chromatography, it can be interesting because we have quick mass transfer, we have low diffusivities, lower viscosity, so we can go faster in the columns. The consequence of this is the ability to reduce the columns, the amount of stationary phase on the column side. CO2 is relatively cheap as a solvent compared to other organic solvents. But if we want to do chromatography at very large scale, these are not the two main factors. The main factor is dilution, and dilution and the choice of the solvents that are used for chromatography are definitely the key factor in the optimization. So the answer, if we want to use CO2 in chromatography, is really, is it the right solvent to minimize energy? And when we look at industrial attempts to industrialize chromatography, a lot of them actually are not used. The one on EPA, DHA is definitely not very efficient if we use only CO2, because you need very, very high flow rates compared to liquid chromatography. And there is a lot of interest today in purifying cannabinoids and using chromatography, CO2 chromatography. But again, I will not give the answer here as we are recorded. But this is the question: is CO2 alone the good solvent? When you use chromatography with CO2, what is observed is that actually we use a lot of co-solvent to make it a right elution solvent for chromatography. And it is quite frequent that we use co-solvent up to 20 or 50%. And here comes another drawback of supercritical chromatography at preparative scale, because like in extraction, we have to collect product. And here we collect the product diluted in the co-solvent. And when you look at thermodynamic equilibrium in the fractions that we are collected in the liquid phase, you get a lot of CO2 that is dissolved in these liquid solvents. When looking, for instance, at ethanol at 50 bar, you get between 30 to 50% of CO2 dissolved in liquid ethanol. So all this is a waste, and these are huge quantities of CO2 that are wasted compared to a liquid chromatography. When you are recycling all the solvents that is going out, you are just making a distillation of all of it. So you get recycling factors above 98%. Here it's far from being the case. It is cheap, but it has an impact, energetically speaking and carbon footprint speaking. So this is why we try to optimize the dilution, and we have been developing the simulating moving bed, which is a continuous way to make chromatography to reduce the dilution. In this mode, we inject continuously the mixture, we flow CO2 or diluent in one direction, and as we cannot move the solid, we just switch the feeding point and the collection point periodically, so we can simulate a move of the solid switching the collection, the injection and collection point. And this way, instead of using batch chromatography, where we collect the product at different times and we can repeat the injection and the collection versus time, here we inject continuously, we collect continuously. So inject the mixture in the middle of the series of columns, and we collect concentrated extract at one point, concentrated raffinate at the other point, and basically, like in many processes in chemical engineering, going continuously, basically, if I want to summarize, allow to minimize dilution and to maximize energy recovery. So going back to example of EPA purification, when we developed the EPA purification at above 99%, CO2 has not been chosen because it was not economical, it was considered not being the best solvent. And the process has been developed in the 90s, first with molecular distillation and then supercritical feed fractionation, and then using liquid SMB and batch chromatography to purify these omega-3 ethyl esters. So very big column has been built in the south of France for this application. And recently, the supercritical fluid simulating moving bed has finally been developed. We don't use fractionation to enrich the EPA to 60%, but we use supercritical fluid simulating moving bed to enrich it to 97%. And we find again the advantage that I mentioned at the beginning of using smaller columns, of having a better productivity thanks to CO2, because we can concentrate more and go faster on the stationary phase. But if we have to be honest, the biggest efforts that have been made is choosing the right mix between solvent and CO2 to have the best solvent to make this chromatography and optimize also the CO2 recovery in the fraction collection to minimize the CO2 collection. So today we can say that this process is economical, and if we don't make these efforts on optimizing the solvent and optimizing energy recovery, we would have to go back to liquid chromatography. Going continuous is also a way we try to develop in the crystallization and particle formation process. I don't know about the time, but I don't want to detail all of them. You can use CO2 in different ways, either as a solvent, and then you depressurize to form some powders. You can use CO2 as an anti-solvent to dilute a liquid solution to crystallize a solid. These two processes, because of low solubility or because you both have to use it as an anti-solvent, then to spray, then to dry the powder, usually bring to very high dilution. And this is only used for pharmaceutical because this is very costly. The one I want to detail a little bit is what we call PGSS, where you use CO2 to melt an excipient, a polymer usually. So using CO2 allows to decrease melting temperature, and basically you will use a batch of a reactor where you will melt this polymer. You mix a product to be encapsulated, and you use also CO2 to spray this high pressure. And here you got very nice solvent CO2 over feed ratio, and this leads to a nice application. When you have an active principle, it can be a protein that you want to protect with an excipient. It can be a flavor that you want to control the dissipation. So you have several fragile molecules that you want to control the delivery and that you want to protect with an excipient. Basically, you have a mixed reactor where you are mixing all this under pressure with CO2, and then you spray it in an atomization vessel. This is a bit complex because it's you have to master the mixing condition, and it's very difficult to control the transfer from a high pressure condition to a low pressure condition when you don't control the quantities. You control the initial quantities, but you don't control right after you open the valve in this batch vessel. So using this in a batch mode is quite complex. So this is why we developed it at large scale, trying to make it continuous and introducing continuously exactly what we want to have at the exit, with controlled flow of CO2, controlled flow of the melted excipient, using it at high temperature, but basically the mix is done at lower temperature, and introducing the active principle to be protected continuously or almost continuously. So we introduce the three of them independently and continuously. We mix them and we spray them continuously. And going through a continuous mode allowed to obtain a process that is much more robust and much better controlled for this very attractive process of particle formation. The last one I want to introduce is aerogel formation. I know Pavel will speak of it, so I will leave him detailing more in detail, but we are also working a lot on aerogel formation, drying of a gel with CO2 to make insulation material, very high quality insulation material. It exists in form of blankets like this, but what we do at KI is making basically powders and beads of fine particles of aerogel that can be then introduced in some insulation material to be used in construction or in the insulation barrier for be introduced in the batteries of cars. These are two very growing markets, and the demands are huge for these powder aerogel to be introduced in insulation material. And we, again, on this industrial project, we took a quite classical chemical engineering approach to optimize thermodynamics. It's quite easy here because we just remove a solvent like ethanol, so it's quite easy to optimize this. But we have been working a lot on the optimization of the diffusion and the mass transfer using fluidized bed dryer, and working also a lot, like we explained on the CO2 recycling loop, to minimize the energy requirement, because this is the key. We are producing relative low cost material, and CO2 recycling has to be optimized. So we patented a process quite some years ago that is fully continuous, but that is optimizing each step of the process independently, because if we make everything continuous, we have several steps. A gel formation using a process in high pressure, high temperature water. Then we make the beads under pressure. Then we exchange the solvent with ethanol. Then we dry the solvent with CO2, and then we depressurize and we exchange the solvent CO2 with nitrogen in a second fluidized bed column. And we have recycling. I can't show all the recycling here that have been developed later, but basically we are recycling CO2 here, we are recycling nitrogen, and we are recycling ethanol in a different loop. So every solvent is recycled. We have a fully continuous process, a way to optimize each step independently. And we, after about 10 years of development, we are launching at the moment the first production batch of these beads of dried aerogel to be used in insulation material. So I will leave Pavel introducing further the concept, but I am of course open to questions. My conclusion of this talk is that CO2 technology, we try to to convince that it is an interesting technology that is sometimes green because CO2 leaves no residual solvent, that leads to very interesting products like these aerogel materials, that is sometimes affordable when CO2 has the right properties, but with limited application. I don't believe it will be so widely spread, widely used, because CO2 is only used when it can bring good solubility. Otherwise, we have to use the right solvent to make the right energy management. Always think of the other interesting properties of CO2, like the good mass transfer. There is as I was saying at the beginning, CO2 is used also because of the marketing. But because of this, a lot of mistakes are still made, and CO2 is not always wisely used. So as chemical engineers, we need to advise on this and to apply the overall chemical engineering procedures and systemic thinking and energy optimization, like in all other processes, to make it sustainable. The only difference is that we have to use these specific tools to obtain the right data. However, we can pretend that CO2 is already a mature and industrial technology. Judith showed it at the beginning. But as chemical engineers, we still have a lot of work for improvement of this, and bringing this process continuous is one way to make it more economical and more sustainable. So thank you for the attention. I'm open to questions with this general email address. Thanks again.
Many thanks, Jean-Yves, for this great presentation. It was really nice to learn from your slides about scaling up of high pressure processes involving supercritical fluids. So many thanks. We have, let me see, here is one question. Are there any LCA studies that support the claim of supercritical CO2 extraction being greener than other processes aimed for the same purpose?
Of course, there are. There are not so many published, to my knowledge, but in my role of chemical engineer industrializing it, all customers obviously ask and do LCA. It's not always obvious to make. And just one example for estimating the carbon footprint of CO2, it's very dependent on how you produce CO2 and where you use it. So CO2 can be taken from ammonia plant, where you have a relatively low CO2 footprint impact. It can come from bioethanol, it can come from the ground, it can be burnt, then it has to be purified, it has to be liquefied, transported, and depending on your supplier, depending on where you use it, the carbon footprint impact can vary from 100 gram per kilo of CO2 that you use to 1,000. So you really have to take all these parameters when you do such a life cycle analysis. That's the same for energy. It depends, of course, on where your energy comes from. More and more customers are asking for electrical energy, and you can produce heat from your chilling machine that is producing the cold water. So there is a lot of energy optimization here to optimize and to make it more sustainable and to bring the right value for LCA. And from my experience, there are a lot of processes that are not so good in terms of LCAs because everything is not optimized. So this is definitely a requirement.
Thank you very much. Before we continue, here is information for participants. So please, you can, during presentations also, you can write your questions that will be answered at the end of webinar. Unfortunately, our sixth presenter, Professor Tarek Abu El-Mati, was prevented to come here today. His absence is not by his will, so we really hope that we will have his talk in some of our next webinars. So we are still in time and we will have some time to answer to questions also at the end of the webinar. And now we continue with Professor Pavel Gurikov from Hamburg University of Technology and Engineering of Porous Materials. Pavel, welcome. The screen is yours.
Thank you very much, Irena, and thank you very much, everybody, for inviting me. It's a great event organized by European Federation of Chemical Engineering. I'm very proud to be here. My name is Pavel Gurikov. The title of my talk gonna be Engineering of Porous Materials from Microscale to Application, and I really want to now bring you a little bit more understanding what we mean by engineering, because when you read literature, you often have very mixed up definitions of what engineering is. We actually understand engineering very broad, and microscale aspect of engineering, what is often called material engineering, material science, is one aspect, is about manipulating of molecules, objects, polymers to discover and invent new materials. Of course, to characterize them, to define their properties, and so on. But there is another side of engineering, what is often called in English process engineering, and this, of course, is about fabrication at large scale, and is not only about chemical engineering in particular, but of course we want to take everything what we have discovered in microscale and to bring it into the fabrication workflow to come up with the material which is which makes our life better, basically, which make our society better place to live. So as you all know, fabrication often begins when we're still lacking data on micro scale, and I want to convince you also that the deeper we go at micro scale, the more we can gain for fabrication process and vice versa as well. Yeah, and the simple reason for the vice versa process is as soon as you have established fabrication, but not even understanding in full details, then you have material in hand, you can come to people and say, look, I have a material which has very interesting property. Maybe I don't understand fully how it's made, but still it is here and I'm able to produce this at large scale. So it's not always a very straightforward relation between all these four aspects which are given on the slide. Let us a little bit focus our discussion today on porous materials, the porous materials which contain air. That's what I'm going to talk about. They all are around us basically, and the couple of examples are given here, ranging from filters to sugar cubes, also paper, the wood itself. Many of them are intrinsically porous, or we make them porous. I want to narrow down our discussion today by to the very special class of materials, which is called gels. So materials which everybody of you can produce today on Friday. So if you want to cook something, you know, you take a teaspoon of gelatin, you put it in 100 milliliters of water, then you heat it up, then cool it down, and then what you end up with is a very solid material, which is called gel. It is again a material, is a soft matter kind of material, which contains a little bit of solid and a little bit of liquids, but it does behave like a solid. And you all know these examples, ranging from synthetic polymers, from biopolymers like pectin, like starch, like alginate, agar, and so on. And even some objects, living objects, also look and function as big porous machines. So what happens if you want to take all the liquids out of this soft material and to make a solid replica of this? And of course, your natural intention, your natural modus operandi is you just take this material and then try to evaporate this liquid out of this soft thing. And then unfortunately, what you're going to experience is what we call capillary pressure, capillary forces, is an unavoidable phenomenon which happens in very, very small pores. And that's what actually, this gives me a very nice opportunity to tell you that all these porous materials, gels, are made out of pores, and the liquid, water in many cases, but not necessarily, occupies the space in these pores. And as soon as you start taking out this liquid, you have a very unfortunate phenomena for drying, that the meniscus here, the phase boundary, is not flat. And this basically means that you have difference in pressure between the gaseous phase and the liquid phase. And as soon as you have anywhere the difference in pressure, then this pressure is going to do something to your structure. And this capillary pressure is exactly the same thing. It's going to collapse your structure. And if you try to dry any gel or an apple or, for example, grape, in an oven, and you see how quickly the structure is going to be collapsed, is also applicable to chemical gels. This is a nice example of silica gel, hydrogel, which is being dried and then loses all this nice properties. What are we supposed to do with this? How do we bring the wet gel into a dried gel state? And the answer is, because we're in high pressure section today, the answer is to use high pressure technology and use a very nice and very powerful fact that liquids and gases do coexist, but only in a limited range of pressures and temperatures. As soon as pressure and temperature are exceeding so-called critical point, then you land in a place which is called supercritical region, supercritical fluid region, where there is no difference between liquid and the gas. And if you slide back and take a look, I have liquid here and gas here. Indeed, that if I bring this liquid into the supercritical state, then I don't have any capillary pressure anymore. And that's early, in 30s, last century, people have done this and have repeated them later on after approximately 50-year delay. So they've taken a gel, brought it in high pressure vessel, put an extra solvent on top, and then heated up everything just to be somewhere here during the process. And then they slowly let the solvent go out to avoid having liquid phase in your material. And by doing so, they managed to produce what is still fascinating me. Or anytime I'm entering the lab, unfortunately, I'm not longer so often in the lab, but as soon as I have opportunity to touch, to feel, to smell any new type of material, which is called aerogel, I always do so. And this is example of silica material. You see how light it is, and that simply has the reason because you had very little amounts of solid and a lot of liquid. And if you manage to extract all this liquid out, then you will end up having this porous structure. If you're able to unfold this, you will get huge surface area. We call specific surface area, how many square meters of surface available in such structure per gram. People don't do it in the way I just explained you. They do it in a different way. And thank you very much to all the speakers which been presenting before me. They laid foundations which I don't need to explain. So basically, we take a gel which contains a liquid which is miscible with CO2, with carbon dioxide, because carbon dioxide has very moderate critical temperature, critical pressure. And many solvents are miscible with CO2, and they form supercritical mixtures. And that gives us a fantastic way how we extract solvent, which is depicted here as green, with CO2 working just above the critical pressure and critical temperature for the corresponding mixture. So that's how you basically bring this high temperature supercritical drying into the so-called low temperature supercritical drying, the process we use extensively now to produce porous materials out of gels. So Summarizing this short introductory part, so we have basically 4 steps or 3 steps, if you will. So we have a gelation step. We produce a solid but still wet material. We have sometimes to substitute this water if the reaction goes in water by an alcohol, for example, and then they extract the solvent alcohol to make a porous replica of the structure here. And of course, as you as a chemical engineer, you may ask, all right, here's a chemistry part, but here solvent exchange and supercritical drying, they do sound like 2 extraction processes, and this extraction takes place within the porous body. So it has basic balls and and the pores and the channels, which all make the process diffusion controlled in many cases. So, and you may wonder, because I have to use high pressure here, I have to do an extra step before, how fast it goes, how much resources I need, how much CO2 basically I need to produce 1 gram of this final material, how much ethanol or other solvent I have to use, what is the smart strategy to go from this state to that state. And this all about implementation, about duration, and later on about scale up. At the gelation step, of course, you can also pose questions which are more of a chemical nature. How do I control and tailor the microstructure of the gel for specific applications? That's all questions I'm going to tackle in the coming slides. Good. So a naive approach would be, then you take the diffusion equation, write it in a proper coordinate, and say, okay, since extraction, the supercritical drying is nothing but an extraction, but you're not interested in extract because as a solvent, you're interested in raffinate, which is left in the autoclave in a high pressure vessel after the drying. Why not to apply simple fixed low diffusion description? And as you see, and that's very well known in the literature, that you in many cases during the process going to be off. Sometimes you overestimate, sometimes you underestimate how much solvent you extract. And then of course it does matter, because you want to bring the drying to the very end. You want to extract as much solvent as possible. So obviously this type of equation and this type of description is not complete. It is intrinsically incomplete to give you a correct answer. But to your, for your creativity to go off, you of course need some experimental data. And for a long time, such data were missing. And only recently with our partners, with Andreas Breuer and his team around him, what we realized that we have to really look into the gel to be able to say, okay, here at this particular place, I have this and that concentration of the solvent and CO2. In other words, you have to specially resolve the concentration profiles within the gel. And with this information, you can start to model basically these things. So I don't want to enter into details of the modeling. So just give you, a flavor of what you've done. So basically, as any chemical engineer, you tend to begin with something which is very, very simple. For example, cylindrical shape. So you can produce cylindrically shaped gels, and you can write down all the equations for this case. Then you may also say, okay, what about particles? In many cases, I need particles. So maybe one particle is a little bit too small. What happens if I put the particles in a fixed bed? And then you can also do an experiment with fixed bed particles and see how fast the drying goes. And with this all these 3 cases, then you can be pretty sure that you basically can describe any geometry you want. And as I just mentioned, you in some cases have to use the advanced analytical techniques, which in our case was Raman spectroscopy, to resolve the profile and later on to validate the model. Why intrinsically diffusion approach does not work? Because simply, if you explain it in a simple way, the diffusion coefficient during the supercritical drying is not constant. The flip side of supercritical fluids is not contrary to conventional media, is you can control pressure and temperature. So in conventional media, like for example, organic solvents, you only control temperature. But by varying pressure and temperature, you always have a very, very special type of behavior, and the diffusion coefficients are always, and all other viscosity, for example, they all function of pressure and temperature, or we sometimes say density and temperature, or pressure and density, two independent variables. And the diffusion coefficients, no matter what what coordinates you're working in, is a function of this process parameters, and you have to take it into account. Another complication is that you have this lovely term, this is the porosity divided by tortuosity, that basically describes how difficult for me it is to go through the gel, because gel is not a stationary media. You have walls, you have to diffuse through this, and that reduces your diffusion coefficient. And if you this all take into account, you still will end up having a purely diffusional approach, maybe a little bit more sophisticated. For a real situation, to be able to describe a real situation, you also have to take into account convection and the mass transfer in the between the single particle or single cylinder and the bulk phase itself, and that is usually done with the mass transfer coefficients. If you put all of these things which I just quickly described and properly describe mixture properties, because you go from pure solvent to pure CO2 to between two extremes, and that's also challenging how to describe mixing properties. And then you find a proper way how to solve the numerical equations like this, then you're gonna get things which you can compare later on with experiments and see which parameters I have to fit. So basically, in our case, we find out that only two parameters you have to find from the literature or to fit are these two. They are intrinsical parameters for the gel. So they describe nature of the gel. And instead of giving you validation, all these things, I just want to show you one thing which any chemical engineer cares about. Very natural question you may ask, okay, if I make gel particles very, very small, what happens? If you make them small, then from the diffusion limitation case, you go to the diffusion in the bulk phase. So then the flow of the CO2 coming and facing the gel will matter, because you can increase the drying rate by increasing the flow rate of CO2. But for very big gels, of course, and that's what we can also visualize very easily, it doesn't really matter whether you do it fast or small or fast or slow. The diffusion needs its time. Second thing you may ask, how much CO2 I consume in all these cases? And this model gives you, of course, a very natural answer, because you always, have the mass transfer, the flow rate of CO2, and then you can easily recalculate how much CO2 you are to introduce into equipment. And with this data, you can begin what we first call, instructions, or just playing with the model to see what happens if I change this and that parameter, what happens if I change temperature, pressure, what happens if I change size, and all of them. And then, of course, you naturally move towards scale up. And with all this knowledge, and I have to be honest here, so of course, that you have to be ready also to go sometimes blind. You don't need to wait until this knowledge is here. You go and produce big batches, and then you simultaneously do simulations, and then you merge this data to be able to produce large batches. Our philosophy at the TUHH, at the Institute of Professor Smirnova, where I'm working, is to go also one step further, to make big batches of materials, just to test these materials, in particular biopolymer aerogels, which you see on the slide, in industrial environment. That's the key logic and philosophy behind what we do. Of course, we do interested in also in microscale, and we ask ourselves, okay, do I have to dry what I get? Do I take the gel and then just make aerogel out of that? Do I have any decrease of freedom to control the microstructure? Because it's also important which microstructure you have for application. And the answer is much more complex than for typical chemical engineering problems, because basically here you rely on modeling. And the only thing I want to tell you about modeling, the more deeper you go, the more sophisticated it gets to model realistically things, for example, like gel formation. Why? Simply because they take place at different scales. So you see a typical hydrogel structure. So the hydrogel contains these fibers, and the fibers are pretty small. And what your modeling can access is only a tiny part of this, maybe 50 nanometers, as in the case here from the literature. So you may see only formation of one maybe or a few single fibers. So you can't really model the entire structure, but it does matter. We want to know how pore size distribution is, how, thickness of the fibers is, all these kind of things. So it's still out of grasp currently, and of course with the novel developments it may become at some point possible, but our philosophy is a little bit different. So we do want to go towards what we call coarse-grained modeling. I don't want to dive into details. I just want to say that we represent polymer chains in a simplified approach. We take care about the chemical nature of the polymeric chains, and what we do, we let them move according to physically motivated laws, and we see how they merge together to form gel structure. And depending on the composition, which is here denoted G and M, it doesn't really matter what exactly it is. It's just two residuals, sugar residuals along the chain. You may ask yourself, what happens if I just substitute this G by M or this M by G? What happens if I change the chemical nature of the polymer I'm dealing with? And from the experimental results, you always know that when you have this high G, then you have more, more porous structure, and then you have low G, the mesh size is kind of smaller. And you can always validate this against the experimental data and say, okay, then I have a tool. I have basically a rocket in hand, which I can use in a reversed way. I can ask myself, if I need a certain structure, a given structure, what should I do in the gelation process to get to this place? Yeah, of course, takes much more computational effort, as you can imagine, because you have to, enumerate and test various parameters. But it is principally possible, and that's basically the core research of my group, to develop such models, to validate such models, and then to use such models to be able to come up with a rational design of porous materials. So as you see here, the structure containing these four building blocks are not as simple. So there is always crosstalk between these two scales, but there is also another crosstalk between application and fabrication, simply because of, for example, price. In some markets, you can go, for example, aerospace technology. You really don't care about price. In some cases, for example, construction industry, where the market is very much established, you have to reduce price as low as possible, and so on. So there is no straightforward workflow how to come from idea in the lab to the application. And that, of course, makes me difficult to discuss applications in general. That's why I decided to go for one particular application where aerogels are very well known for, namely thermal insulation. So if you Google aerogels, you're going to see pictures like this. That's basically they aim to show that aerogels are great thermal insulators. And why it is so? The simple reason I love this cartoon, the simple reason is because the air convection is very greatly reduced in the porous material. And this cartoon basically shows this. Yeah, you see the air molecules are constrained within the small pores. And what happens, they are not able to efficiently transfer the heat by collision, by molecular collision, from one side of the heat source to the opposite side. And aerogels are the best materials in the class. And with all this, you may wonder why we don't commercialize these things. And the answer, we do commercialize. 2021, we founded a company which is called Aerogelit to be able to combine the best from all the words which I just present you into one single class of materials. And the motivation behind was, okay, we know that conventional classical thermal insulators are fantastic materials, but they lack renewable content. There are also materials which are of very high renewable content, but they lack performance. So basically the thermal conductivity of cork or wood fiber is very, very high. If you go to high efficiency thermal management in houses, for example, then we can't rely on these materials, but we can not also rely on synthetic materials because basically we are limited by crude oil. And that's why we wanted to have something, the best from two words, and we went to develop a family of biopolymer-based aerogels, which of course have a very, very high renewable content, and it's very, very challenging also to get to the place where they have very high insulation performance. We managed to do this, and that was only possible because we also have a long academic track being supported by fundamental research. So just the last slide before I conclude, this is our team. If you're interested in what we are doing, you can always check out our web page. At this point of time, I think it remains me just in the interest of time just to say thank you very much for your attention. I hope that I was able to give you an impression of how this all goes. If you have specific questions, a couple of email addresses are given here, so drop me a message. And I'm looking forward to a lovely discussion now or later. Thank you.
Thank you very much, Pavel, for this great speech. At the moment, we don't have questions, but we are open until the end of the webinar. So we will proceed with our last talk from Professor Sabine Gruner-Lempert from the University of Applied Sciences, Weihenstephan-Triesdorf. The lecture is about natural antioxidant powders. Sabine, welcome.
Thank you very much for your kind introduction, and well, thank you for giving me the opportunity to give this presentation today, and thanks a lot to all the speakers before explaining all the theoreticals to the supercritical fluid, so I can quick through. So my talk is about antioxidants from plant-based materials and to get the antioxidant power, and we transfer these antioxidants to powders to make their application much easier. I selected 3 examples, so 3 different plants and different ways to get products from them. The first one is the rosemary plant, where we get high pressure extracts from. The second is the amaranth plant, and the third is the rooibos tea plant. So let's start with the rosemary plant. I think everybody of you know the rosemary plant, and well, it contains really powerful antioxidants, which are luckily good carbon dioxide soluble, so it's easy to get extracts from them. And the ingredients which are valuable are at the first carnosic acid, followed by carnosol and rosmanol. And these are all phenolic diterpenes, which can break the chain reaction during the peroxide oxidation or the oxidation of unsaturated fatty acids just by a rapid donating of a hydrogen atom to the lipid-free radicals. It's a well-known process, so this is a typical act of antioxidants. And to get a concentrate of these antioxidative ingredients, we do extraction process with supercritical carbon dioxide before there is a grinding of the rosemary leaves with liquid nitrogen, because we have to avoid temperature and oxygen stress before the extraction, because then we would lose a lot of ingredients. Normally, the carbon dioxide extracts of rosemary are solid materials, which are not so easy to apply in many products. Therefore, we generate a fine extract powder using the PGSS technology. And this fine powder is easy to apply afterwards. I'm sure everybody of you is familiar with the high pressure extraction, therefore I go quick to the process. You see the extractors where the plant material is placed and the liquid carbon dioxide is heated and compressed to the supercritical state so that it can flow through the plant material and solve all the ingredients which are soluble at the chosen extraction conditions. Then afterwards, we depressurize and get one, or in this case, 2 extracts in the separators. And the carbon dioxide is recycled, so it is cooled down to the liquid state and transported back to the storage tank. You have heard about the PGSS technology today. I just want to explain it in a short way. PGSS is the abbreviation for particles from gas-saturated solutions. What we do in the PGSS technology is quite easy. We take the rosemary extract and the carbon dioxide, and both substances were fed to a static mixer to make the process continuously. In the static mixer, they are mixed intensively. Carbon dioxide is dissolved partly in the rosemary extract, and then the pressure was released rapidly to atmospheric pressure, and fine droplets are generated and finally solidified by the low temperature and by the released carbon dioxide. So at the end, we get a fine powder in the spray tower and maybe a fine dust fraction in the cyclone. These products are then, well, widely applied in the food industry, especially for the protection of fats and oils in the product, because you have heard the ingredients can protect the foods for against oxidation. They can avoid rancidity. They can avoid the decoloring of natural colors. And therefore, you find a lot of products in the market where you can find the rosemary extract inside. So you see here sausages, ham, burgers, croutons, potato chips, and so on. You just have to look at the backside of the food product and you can find the rosemary extract labeled there. If we compare rosemary extracts with alternative antioxidants, like the synthetic ones BHT or BHA, or a natural one like alpha-tocopherol, you can see that the ingredients in the rosemary extracts are much stronger. Here, there is a test performed where we measure the peroxide value at a stress at 120 degrees Celsius over a time period up to 30 hours. Animal fat was mixed with different amounts of antioxidants, and you see here in this case the alternative antioxidants, a ratio of 0.02% was added, and in the case of rosemary extract we chose half of the concentration. A low peroxide value means that the oxidation is not so strong and we have a low peroxide value and no rancidity in the product, and a high value means that we have a strong oxidation. And you see from these results that both rosemary extracts have a very strong antioxidative capacity and avoid the rancidity or the oxidation in a good way. To give you an example here, we have a sensory assessment with cooked sausages, which were stored over a time period of 35 days. The light green bar stands for the sensory assessment of sausages with rosemary extract, and the dark green bars stand for the sensory assessment of sausages without rosemary extract. And you can see clearly that after a storage time of 35 days, we have a high rancidity result in the case of sausage without rosemary extract, and we obtain the quality and the good taste in the case of sausages with rosemary extract. And if you look at the active ingredients in the sausages, you see there is a degradation of the active ingredients, the antioxidants, but we have still more than 90% still there, so the storage time can be prolonged further. Let's come to my second example. This is a high-pressure seed oil from the amaranth plant. Maybe you know amaranth. It's one of the oldest crops in the world, and it was a holy plant of the Incas and Aztecs. And it has a good, positive image because of its unique ingredient composition. Especially if we look at the seeds, we can use all parts of the seeds, but today I want to highlight the oil because it has a real high amount of unsaturated fatty acids. The seeds contain oil up to nearly 8%, so it's a really high oil content. And we get this oil to avoid oxidation or quality loss by extraction with supercritical carbon dioxide. Before we use a grinding with liquid nitrogen, you already know why, to avoid oxygen and temperature stress. And the final product is a light yellow oil, which can be used as in liquid form or can be used in as a fine powder. But before I come to the generation of the fine powder, I want to highlight the ingredients of this amaranth oil because it has one unique ingredient, which is called squalene, and a lot of unsaturated fatty acids, vitamin E, and phytosterols. Special is the squalene, which is a triterpene with a high antioxidative effect. It prevents against arteriosclerosis or cardiovascular diseases, empowers our immune system, and the recommended daily intake today is between 50 and 500 milligrams, depending on you and your, if you make a lot of sports or what is your weight and so on. Squalene, by the way, was discovered in 1906 by a Japanese researcher, and he discovered it as the main component of the shark liver oil, especially in the species of Squalide. Unfortunately, millions of sharks are slaughtered, therefore, just to get the liver. And the rest is, well, the living fishes are just thrown back to the sea. I'm sure you know these horrible pictures, and you find a lot of food supplements in the market. If you look for squalene or shark liver oil, you can buy them in capsules, you can buy them in oil or any other food products. And we're really happy that with the amaranth, there is an alternative source to the shark liver oil, and it is plant-based. And it's a a really interesting alternative, because if you look at the squalene content, which is given in this diagram, of plant-based oil, you see that the amaranth extract has an outstanding position because it has a much higher content of squalene compared to all other plant-based oils, which are known as squalene-rich oils. Yeah, but here we are below 0.5%, and the amaranth extract has about 7% squalene. So this is a really economic alternative to the shark liver oil. So if you can't use the oil directly in the product and you need a powder form amaranth seed oil, then you can use the CPF technology. The process is quite similar to the PGSS technology I explained before, with one exception. But first, CPF is the abbreviation for concentrated powder form. Similar to the PGSS process is that we start with a liquid and carbon dioxide, and both were fed to a static mixer, and there's intensive mixing. Carbon dioxide is dissolved partly in the oil, and we get a fine spray during the depressurization up to atmospheric pressure. And we get very fine droplets in an oxygen-free atmosphere and at low temperatures. In these fine droplets, we add now a carrier material which is bound to the liquid and forms a fine powder, which is finally released from the spray tower. The carrier material can be any kind of a powder: starch, cellulose, sugar, silicic acid, and so on. So there is no limit. The carrier material just influences the amount of oil you can add. Because of its unique effect to skin, amaranth oil is applied in cosmetic products. For example, in eyeshadows, if you use the CPF technology, you can include a high amount of amaranth seed oil in an eyeshadow. Up to 12% is possible. And it is known from a lot of scientific studies that there is an anti-inflammatory effect to the skin of the leaf-on products if you have 5% of amaranth seed oil inside or more. And this is especially suitable for people who suffer from psoriasis or atopic dermatitis. So this is a really good product for those people. So we come to my third and unfortunately last example. Of course, I can talk about hours about antioxidants in supercritical fluids, but today I will close with a third example. And this is about the rooibos plant. Maybe you know rooibos tea. Rooibos is a bush which grows in South Africa. It's a traditional tea plant, and it is scientifically known and written since 1775. And it grows only in the Cederberg region in South Africa. It has not only in South Africa a strong positive image because it's a caffeine-free tea and a very healthy beverage. And the reason is because of one component. It's a flavonoid called aspalathin, and it's the main active ingredient in the rooibos plant. It has a lot of effects. You see here: antioxidative, anti-inflammatory, anti-allergic, antimicrobial, and scientific studies show that it also enhances the well-being. And to get yet this aspalathin as a high concentrate, it is necessary that we use green rooibos leaves. I explain it in the next slide why. There's also a grinding with liquid nitrogen, and then we do not a high pressure extraction with supercritical carbon dioxide. We do a solvent extraction, at atmospheric pressure, but a two-step extraction to concentrate the S-palathine in the final extract. Because of the fact that S-palathine is not very stable in liquid extracts, we do a PGSS drying, so it's a supercritical drying process with carbon dioxide to get very fine powders at the end. And these are stable, so they are storable over years, and they can be easily applied to a lot of products in food, dietary supplements, cosmetics, and so on. So let's come to the green rooibos leaves. Normally in South Africa, the farmers dry the leaves in the sun, and there a fermentation takes place. And the fermentation leads to the well-known red color of rooibos leaves and also to the well-known sweet flavor of rooibos. But as you can see from this chromatograms, unfortunately, the fermentation leads to a great loss of our valuable ingredient S-palathine. Due to the fermentation, we have a loss of 90% of the S-palathine. So it's simple gone. Therefore, it is really necessary to use the green leaves. And to give you an idea about the strong antioxidative capacity of rooibos extract, I have here a result from a study where we compare different antioxidants or antioxidative extracts, plant-based, like green tea, our rooibos tea, honeybush, and the rosemary extracts in 5 different test studies. And you see, if you look at the rooibos extract, we have excellent results in all our tests. So it is a really powerful antioxidant. And therefore, it is used in a lot of applications. In South Africa, it is well known, and there are hundreds of products in the cosmetic side, especially for leave-on and skincare products. In Europe, for example, it is more, or it is better known in food products, especially in dairy products or in beverages. But if you look at the World Wide Web, you find thousands of products, including rooibos, but you really have to look if there is a green rooibos extract inside, because then you have a high antioxidative potential and you have a high active ingredient inside. So I'm still at the end. I hope I could inspire you a bit dealing with plants, dealing with antioxidants, and compare it with the supercritical fluids, because with them we can really achieve high quality products with a high antioxidative power. I say thank you for your kind attention, and of course I want to thank to a lot of people who were involved in the scientific studies and in the scientific work over the last decades. Thank you.
Thank you very much, Sabine, for this great presentation and information about the application of extracts and powders. Altogether, today we learned really a lot about high pressure applications, and for that I would like to thank to all participants for being here and all speakers for these great talks. So huge thanks on the behalf of the Working Party on High Pressure Technology. At the moment, we don't have further questions, so we can conclude our today's meeting with information again that all information, so this is taped, and we will have this webinar available on the YouTube channel of the European Federation on Chemical Engineering. and information that next Spotlight Talk series will be organized next spring, and we will keep you informed about that. So many thanks for your presence, and see you next spring on new Spotlight Talks. Goodbye.